everyone, I hope you all are doing well. In this video we are going to solve the problem 4 from chapter 5 of solid state physics by Kittel. Actually, Introduction to Solid State Physics by Kittel, maybe that's the exact name. And this is the problem 4. I have already uploaded the solutions to problem 1, 2 and 3. The links will be in description box or in comment section. You can check them out if you need. Let's first look at the problem statement to understand what's required in this question, and so that we may make a timeline of what we are going to do in our mind first, and then we'll dive into the solution. So let's see the statement first and then we'll solve it. Additionally, I'll make the chapters in the description box where you can directly jump into the part of the video where the solution has actually started. To me, understanding the question statement is a crucial part of the solution. So I recommend you people to attend that part where we'll discuss the statement and each and everything that is needed here and what everything that is given means to us and so on. So let's start with the statement. So here's the problem 4. It is about the heat capacity of a layer lattice. In part A, it is saying that consider a dielectric crystal made up of layers of atoms with rigid coupling between layers so that the motion of the atoms is restricted to the plane of the layer. As we can see here, that we have a crystal that is made up of layers of atoms, and there are several layers of atoms. For example, you can imagine it like these as layers, okay? And there are several layers of atoms that make up the whole crystal, and there is a strong coupling in between these layers so that the atoms cannot move in between those layers, and they can only move along the plane. Okay, they can only move on the plane, but they cannot move in between these layers. Hence the motion of the atoms is two-dimensional here. The case has been reduced to a two-dimensional case because the motion of the atoms is restricted on the plane, and a plane is a two-dimensional body. So the atoms can move only in two dimension and cannot move in the third dimension, and the third dimension was actually in between the layers. Okay, the direction in between the layers. So the motion is two-dimensional only. So we'll consider a case of two-dimensional body, and we'll have to find out the stuff considering a two-dimensional body or a system under study. Now they say show that the phonon heat capacity in the Debye approximation in the low temperature limit is proportional to T square. So under that condition that is given to us, like the body is two-dimensional, we have to show that the phonon heat capacity in Debye approximation in the low temperature limit is proportional to T square. So we have two conditions here that we have to apply on phonon heat capacity, which are Debye approximation, which we'll see later in the video when we'll be solving the problem, and the second one is to apply the low temperature limit on the phonon heat capacity formula that will generate keeping in mind the Debye approximation. And we'll see at the end that for a two-dimensional case, when we use Debye approximation and after applying the low temperature limit, the formula that we will get will be proportional to T square. Okay, this is simply something that we need to prove, that CV for the given configuration is proportional to T square. Alright, so in part A, we need to prove this one thing. Alright, now let's see the part B, and after discussing the part B, we'll dive into the solutions. It says, suppose instead, as in many layer structures, that adjacent layers are very weakly bound to each other. Now, in part A, we were seeing that the adjacent layers were rigidly bounded to each other so that the atoms cannot move in between the layers. But here we have considered the weakly bound case where the atom can move in between the layers, and hence the three-dimensional motion is now valid. Okay, now it's allowed for the atoms to move three-dimensionally, and the case has been become the three-dimensional case, and all the stuff that will be taken will be in three-dimension. So what form would you expect the phonon heat capacity to approach at extremely low temperature? So we'll be using the Debye approximation again, and we'll apply the low temperature limit again on the phonon heat capacity formula, and we will see what kind of form it will get. So the part A and part B are closely related to each other. The only difference is the dimension of the atom in which they can move. Okay, in part A, atoms can only move in 2 dimensions, that is on the plane, because of the rigid coupling that bounds the atom's motion to 2 dimension. And in part B, we can see here the case is 3-dimensional, and in both cases we had to find out the formula for the phonon heat capacity under Debye approximation and at extremely low temperature limit. So let's dive into the solution. We know that the heat capacity of any system is given by following general formula, which is CV equals dE by dt at constant volume configuration, constant area configuration, and so on. All right, and here the E is the internal energy of the system. And if we know the expression for E for a given system, then we can easily plug that value right into this equation to find out the heat capacity for the given configuration. So what we'll be doing is to find out the internal energy for the system, and after that we'll differentiate it with respect to temperature, keeping the volume or area as constant, and solving it for the heat capacity will automatically get us to the form that we need to prove at first place. Okay, so in both part of the video we have to use this formula. Okay, and we'll be finding out the internal energy for both of the systems that we are given with, and we'll differentiate it with respect to time at the end, and we'll get the form that we need, which will be our final answer, okay, to the question. Now E is given by, for any system, internal energy of the system is given by integration, where E bar is the average energy of the system multiplied by the density of states in F space. Okay, in F as the main variable, I'm taking F here as the main symbol instead of mu. The reason is we normally confuse it with the speed of sound, which is V, or volume, which is capital V. So to avoid that confusion, I'm using F symbol. You can use mu at your own convenience, just to make it convenient for you people to understand the symbols. I'm just using the F. Okay, you can use mu as per your need. So all in all, this is the main formula that we'll be using. Another main formula, let us call this as equation number 2. All right, here d of f is the density of states in F space. df is simply a differential. E bar is the average energy of the oscillators of the system that we have here, and which will be same for both of the cases. Also for the 2D case and 3D case, the formula for the average energy remains the same, but d of f will change depending upon the dimension of the system we are dealing with. And Fd is the Debye frequency. All right, so let us first write now E bar is the average energy of the system, and what we have as a system is the layers of atoms which are behaving as a harmonic oscillators that are having frequencies in the range of d of f. Okay, so the average energy they have is given by hf over e to the power hf by kt minus 1. Here hf is their energy, and k is the Boltzmann constant. T is the temperature, it is the thermal energy, and this is the energy of the oscillator. This ratio is this one thing is closely related to the Boltzmann factor, if you know about it. So there is a systematic way to find out the average energy of any system using the Boltzmann factor. The details of how to find out the average energy and all that stuff is not relevant at the moment to state those details here. That's not relevant. That is why I'm directly mentioning this is the average energy of the system under study. Let us call this as equation number 3. Okay, and density of states For a 2D case, you can write it in words. For a 2D case is given by 2 pi f a over v square. Here f is the frequency, a is the area of the plane in which the atoms can move, v is the speed of sound. All right. This is the formula for the density of states in f variable. Now normally people know the density of states in k space. For example, it is given by a k over 2 pi, and there are the various formulas in different spaces, and it's not possible for us to remember all of these formulas in different spaces. So I'll give you a method to convert the density of states in one variable to a density of states in some other variable or space. So the method will be mentioned at the end of the video. I recommend you people to learn that method of converting the density of states in one variable to other variables. Okay, for example, in d of e, energy as the main variable, frequency as main variable, angular frequency as main variable, k as the main variable. You just have to remember the formula of density of states in one space, and you can easily convert into other spaces by that systematic method of transformation that I'll mention at the end of the video. So stay tuned for that. Don't be confused if you see different kinds of formulas in different spaces. It's easy to convert. So these are the two formulas that we'll plug right into the equation number 2, and let me put it right here. So instead of E bar, which is the average energy, we'll put hf e to the power hf by kt minus 1. Okay, and instead of d of f, we'll write this 2 pi f a by v square, and df as it is. This is ft. Now we'll make a substitution here. Let me put all of the constants out of the integral. Let me write them out of the integral so that the situation gets easier. 2 pi here, this one h here, a outside of the equation, v square. V is taken as constant because in Debye approximation we take the speed of sound as a constant quantity which doesn't depend upon angular frequency or k vector. Okay, it's a constant quantity, and that is why I'm taking it out of the integral. And 0 to ft, only f will be taken as a variable right here. F into f gives f square, this f and this f. Okay, and in denominator we have hf over kt minus 1. This is on the exponent of e. All right, and the k here is the Boltzmann constant. It's not a wave vector. Okay, don't confuse it with the wave vector. It's a Boltzmann constant. You can write a small b in the subscript of k to differentiate it from k vector. So here's the form that we have got. All in all, now we'll substitute something here. This hf by kt will let it to be equal to x. Okay, this substitution makes this integral way easier and will help us to get the form that we need to prove. Okay, so it will make the whole process way easier. Now here we have to convert this integral from f to x. Okay, for this we need to find out the value of f here, ft here, df here, and plug those values right into this integral to convert it into x variable. Okay, for this purpose we need to remove the f from here, and for this I'm taking kt in right here. It will become kt into x, and f would be equals to kt by hx. Okay, this is the value of f that we'll put right here. Okay, the value of hf by kt is x. Simply we'll put it right here. We should know the value of df, which is the differential. We'll take differential on both sides of this equation. kt by h, they will be taken as constant, so simply this is the value of df that we'll put right here, and in place of ft we'll write xt. Okay, ft will change into xt simply. Now let me put all of these values right into this equation to convert into x variable, and doing so will make ourselves closer to the solution. Kt by h, it's kt by h x whole squared as the value of f. Okay, here's the value of f. I'm putting it right here, ktx by h. Okay, divided by e to the power, this is x. Okay, hf by kt was x at first place, so e to the power x minus 1, and instead of df we write kt by h dx. Okay, this kt by h, this kt by h whole square, it will become k square t square x square by h square. It's k square t square by h square x square, and this kt by h again with dx, and 1 over e to the power x minus 1. I'm writing it in a side to avoid any kind of it's k square, and this is k, it will become k cube. This is Boltzmann constant to remember. Okay, don't confuse. This t square and this is t, which will become t cube. H square and this is h, it will become h cube, and rest of all of the thing, oh sorry, it's xt here. Xt, rest of all of the things are in x, that is why they remain inside the integral. Okay, this is the formula for the internal energy of the system, just by considering the Debye approximation in our mind. Another thing that we have to apply on that formula for the heat capacity or internal energy or what else is the low temperature limit. We have to apply the low temperature limit on that formula to get to our desired expression. So for this we have to use the low temperature limit. As t approaches to 0, we have to see what happens to this integral. All right, and for this just remember that what was the value of x, it was equals to hf by kt, and t is appearing in the denominator. And just for a reference, just to have an idea, if t approaches to 0, then what will happen to the value of x is, if you put 0 right here, it will become 1 over 0 type of thing, even if hf by k doesn't make any difference to it, and let's say like that kind of thing, and it is equals to infinity. So as t approaches to 0, x becomes very large. All right, and xt defines it. Xt defines the upper limit to the value of x, the maximum possible x value that the system can approach, and that will be interchanged with infinity. So we'll simply write that as t approaches to 0, xt will approach infinity. Okay, we just have to remove xt from here, and we'll have to put the value it will approach as t approaches to 0 in our low temperature limit. And you can write it right here that as t approaches to 0, we'll see that x approaches to infinity, x becomes very large as temperature gets very low, and we can simply interchange the limit, the upper limit, to be infinity with infinity. Okay, we will do that, and zero to infinity x square dx. All right, now this integral has a particular value, okay, which is 2.404. You can see it in internet. The integration of this integral is a bit tricky thing, so you have to remember its result, which is a constant quantity independent of any variable, because the integral in itself was in a single variable. And yes, this is 2.404. This is the result that we'll get for it, and let me write it right here. 2.404 2 pi h a by v cube kb cube by h cube. I'm just separating the t value from all other values, and all these values are constant. A is constant, v is constant, h is constant, kb is constant. All of these things are constant, and let me write a constant word right here. Okay, just to simplify the case. Now from equation 1 we know that the heat capacity is given by Cv equals dE by dt. Okay, now let me put the value of E right here, and it's constant times T cube. The constant obviously will come outside of the differentiation operator, and it will become like that. And let me derivate, and after derivating it we'll get 3t square as its derivative. 3 is again a constant, will give you constant again. So constant times t square cv, and you can see a proportional result. Okay, cv is proportional to t square. This is something that we needed to prove at first place in part A, and it's proved. In that way the part A has been done, and let us move to the part B of this question, in which we have to consider a 3D case, and the only difference that will arise here will be on the density of states. The formula that we have used previously here, E bar will remain the same, average energy of the system will remain the same, but the density of states will be inserted here for the 3D case, not for the 2D case as in a part A. So yes, let's put the value of d of f for 3D. Let's write part B here, and let me again write the equation number 2, which was for the internal energy. We know that E equals integration from 0 to ft, its average energy d of f df. Okay, E bar, we know that it is equals to hf over e to the power hf by kt minus 1. All right, and d of f is given by, let me see it, 2v f square by v cube, where v is the volume, f is the frequency, v is the speed of sound. Small v is the speed of sound, and capital V is the volume. You can differentiate it from the small v by doing this. Okay, this is volume, just to make it readable for the persons watching it. And yes, now let us put all of these value right into this equation, and we'll get d of f is pf. Now taking all of the constants out of the equation, out of the integral, sorry, and to this h and this capital V, which is the volume, divided by v cube, which is the speed, 0 to ft, f, and this is f square, which makes f cube, e to the power hf by kt minus 1 df. Now we'll do the similar substitution right here. Do keep in mind that this is the density of states for a single mode of vibration. Normally for a 3D lattice, for example, there are 3 different modes of vibrations in which a lattice can vibrate, and if you want to consider all of those modes, then you have to simply multiply the density of states formula for a single mode by 3. Okay, we can do it at the end because it's a constant, and we are just looking at the form that the specific heat will approach as the constant usually doesn't matter what they are actually equal to. Their relation with temperature is something that we need to get, but we'll multiply by 3 at the end of the question to include all of those modes of vibrations. Okay, so we can do that at the end. Now here we'll do the similar substitution that we did before. Let hf by kt, let hf by kt equals to x. Okay, and we'll get h by kt df equals dx, and df will be simply equals to taking all these constant onto here. It will become kt is dividing here, it will be multiplied right here, h will be divided right here. Okay, the value of df is kt by h dx, and the value of f is again kt by h x. Okay, and fd will be simply replaced by xt, and it's a cube instead of square here. That's the difference in that integral. So let me put all of these values right into this integral. It's 2hv by v cube 0 to xt. Now instead of f cube, we'll write kt by h x whole cube e to the power x minus 1 and kt by h dx. It's k cube t cube by h cube x cube kt by h dx divided by e to the power x minus 1 2h v by v cube. Taking these constants outside of this equation, it's k cube, it's k, it will become k4, it's Boltzmann constant, t cube and it's t4, h cube and it's h4. Rest of all other things will remain inside the integral because they are under operator. This one h will be eradicated and it will become cube instead of the fourth power, and kb4 t4 by h cube, and here we go. Now we'll apply the low temperature limit. This is the formula that we have got for the internal energy of a layer lattice considering only one mode of vibration and under Debye approximation. Now we'll apply the low temperature limit on that formula to obtain what we needed to obtain at first place. So now as t approaches to 0, again x will approach infinity for the same reason as we saw earlier. Hence xt approaches to infinity, hence we'll get, let us first write the change in limit and then we'll write now this is equals to pi 4 by 15. Okay, integration of this integral, this definite integral is pi 4 by 15. Okay, this is a definite integral and again it will equal to a constant quantity independent of any variable, so it will be equals to pi 4 by 15. And now 2v by v cube kb4 by h cube pi 4 by 15 pi to the power 4 t4. Okay, this is the internal energy expression, and for all three modes of vibrations, there are actually three modes of vibration crystal lattice waves have. One is longitudinal and the other two are transverse mode of vibration. So there are total of three modes of vibration. A single atom can vibrate, there are the three ways a single atom can vibrate, and that is why we are simply multiplying it with 3. So 3 into 2 will make 6, so 6v by v cube kb4 h cube pi 4 by 15 t4. Okay, there are the several forms that this formula takes depending upon what kind of substitutions you are making. For example, this speed of sound has some other substitution in terms of n and other variables, so it's all up to you what kind of form you want to achieve at the end of this. But this is the internal energy. Now let us derivate with respect to temperature to get the CV expression that we wish to obtain. Okay, all of these are constants and they will come out of this integral. And d by d on t4. It will give us 4t cube. Okay, derivative of t to the power 4 is 4t cube. This 4 will be multiplied with 6, which will give us 24 v kb4 pi 4 15 v cube h cube and t cube. All of these are constants, so CV is proportional to t cube here. Okay, and we can see here that in a 2D case, in part A, CV was proportional to t square, while in 3D case, CV is proportional to t cube at extremely low temperature. So at extremely low temperatures, heat capacity is proportional to t cube, and this is usually called as the Debye t cube law at extremely low temperature, which perfectly explains the behavior of a lattice related to heat capacity, especially at extremely low temperatures. So yes, that is something that we needed to prove, and the question has been done. Here comes the part of the video where we'll learn how to convert density of states in one variable to density of states in other variables. Here we have the density of states formula in k variable for a 2D case. Alright, and for example, I just remembered density of states formula for a 2D case in k space first, and the formula that I'm using requires the density of states formula in f space, for example, in omega space, or in energy space. Then how am I supposed to convert it into other variables? The method is quite simple. This is the transformation equation. Basically, you can see here that density of states in k space times the k interval, differential interval, will be equals to the density of states in omega space times the d omega, okay, differential in omega space. These all products will remains the same no matter what the space is considered. Based on these equations, we can convert density of states in one variable to another. For example, from k space to f space. This is something that we need in that video. So we have d of k dk, that would be equals to d of f df. Now we need the value of d of f, that is why taking df in that side of equation. All right, so we are left with this thing to be equal to, because this equals 1. Okay, so d of f will be equals to d of k times dk by df. Now let me find it for you people, just for an example. D of k equals ak by 2 pi, and keep that in mind. We should first remember at least density of states formula in one variable, then we would be able to convert it into others. If you don't even know density of states formula in one any of the variable, you should at least know the density of states formula in one variable so that you can convert it into the desired one. Okay, so I started it with k variable, so I'm converting it to the f variable. So we have ak by 2 pi as d of k, and dk by df needs to be determined. And keep that in mind, we want the formula in f variable. Here k needs to be converted into f variable too, and for both of these purposes we'll use a similar formula. Also for the substitution of k here, and also to get the value of this expression, we'll use one single formula, which is v equals omega by k. Alright, this is the formula that is valid under Debye approximation, where we assume that the speed of sound is constant and it is equals to the ratio of omega and k, and we know that omega is equals to 2 pi f. This is the relation that we should know, while k remains the same because we want the value of k. Taking k in that side of equation, so v will appear here in the denominator. So k equals 2 pi f by v. Now taking derivative on both sides with respect to f. Okay, so 2 pi by v is a constant quantity as under our assumption. V is speed of sound, which is constant, so derivative will be applied on f, d by df on f, which equals 1. So we are left with 2 pi by v. Now we'll put these values right into this equation. A by 2 pi, k equals 2 pi f by v, dk by df equals 2 pi by v, and 2 pi cancels out. Here's 2 pi f a by v square. Okay, and that was the formula that we used in part A of our video. Similarly, for part B of the video, we can do the similar thing and so on. If you want to convert d of k, please keep that in mind that, for example, we had d of k equals ak by 2 pi by simply putting the value of k, which was 2 pi f by v. You are not converting d of k in f space by simple substitution of k in terms of f. You can't do that. Okay, there is a systematic method. There is a method that you have to follow in order to convert it from k space to f space, for example, to omega space, for example, and so on. You can't simply put the value of k in terms of f right into this equation and you will say that this is the density of states formula in f space. Not that. No, it will not be valid. So you have to use this method in order to do that conversion. Similarly, if you want to convert it in omega space, then simply you will not put the value of omega as 2 pi f. You will proceed by taking this case, this relation onward, and you will get to the form that you need. Alright, this method is similar for any dimensional case. For example, if it is 3D, 2D, or 1D, similar method will be used, similar equation will be used. Okay. The only difference will come in the values of d of k that you will be taking. For example, for 2D case, you will take this. For 3D, you will take another some other formula. For 1D, you will take some other formula. But this transformation equation is same. These basic equations will remain the same no matter what dimension you are considering. Just in case you want to convert into energy terms, then the expression that you'll use, just like you can see here that omega and k are related with this relation, and similarly you can use frequency instead of omega to find the relationship between f and k and so on. But if you want to link between energy and k or omega, then the equation that you can use is E equals h square k square over 2m. Okay, where m is the mass of the system, k is the k vector, okay, wave vector, where you can simply substitute the omega value also if you want to link E and omega. And yes, this is the transformation equation that will help you to plug the value of for example, if you are given with this situation and you want to convert into this, and okay, so d of k will already be known, okay, and it will contain k, which you will put by taking the k on one side of equation and taking all other quantities on the other side, and dk and de can also be formed by derivating it with respect to e. All right, so that's the method. I hope you all people understood the assignment. Goodbye, take care, like, share and subscribe.